Hello students, welcome back to my channel. Today we will study the topics of ring theory. That is, we will study that set of endomorphisms of additive abelian group of integers is isomorphic to the ring of integers and, by example, show that extension ring of an integral domain need not be in an integral domain. Now, let's get started.
नाउ एडिटिव इनवर्स शो करने के लिए what we require for any a comma b in f, इसका एडिटिव इनवर्स कैसा होगा माइनस a comma b। इसको शो करने के लिए चेक करते हैं कैसे a comma b प्लस माइनस ए बी इज इक्वल टू ए बी माइनस a into b square, which in turn implies 0 comma b square। अभी हमने ऊपर देखा था कि 0 of x is equal to 0 of y for any non-zero x and y, and here we know that b is non-zero, therefore it is equal to 0 comma b, the zero element of f, and therefore this is its additive inverse, and hence we have shown that f under addition forms an abelian group. नाउ मल्टीप्लिकेशन का केस देखते हैं कि हमें फील्ड शो करना है इसको। कॉम्यूटेटिविटी कैन बी इजली शोन, associativity can be easily shown, distributive over addition is also very easy. Now we will basically check its unity and multiplicative inverse. Notice x by x is the unity of f. इसको शो करने के लिए हम क्या करते हैं, for x not equal to 0 and x belongs to D, for any a comma b belonging to f, we have a comma b dot x comma x equal to ax comma bx, which in turn is equal to a comma b, as ax comma bx is related to a comma b, which can be seen abx is equal to abx. Therefore, it will act as the unity of f. Now, let a comma b not equal to 0 comma b, the zero element of f belongs to f. Then we notice that a cannot be equal to 0, b तो not equal to 0 है ही, वो हमें already पता है. So we can talk of b comma a in f, and as a comma b into b comma a is equal to ab into ab, that is the unity x comma x, ab into ba, ये commutative है under multiplication, so and it gives us the unity. Therefore, this quantity is our multiplicative inverse, and hence we claim that f under addition and multiplication as defined is a field. Now, to show that f and integral domain is embedded into the field, define a map phi from D to f such that phi of a is equal to ax comma x equivalence class for x not equal to 0 and x belonging to D. Phi is well defined. As we can see, let A is equal to B, then it implies AX is equal to BX, which in turn implies AX into X is equal to BX into X, which in turn implies that AX comma X is relative to BX comma X. That is, they are equivalent as equivalence classes are equal. AX comma X is equal to equivalence class of BX comma X, which in turn implies phi of A is equal to phi of B, and therefore phi is well defined. अब इन्हीं सारे प्रोसेसेस को अगर रिवर्स कर देंगे, then we will have that phi is 1 1. बट हल्का सा रिवर्स जाने के लिए यहाँ हमारे पास प्रॉब्लम आएगी, उसको हम कैसे टैकल करेंगे? That x square a minus b is equal to 0, and since we are talking about integral domain and x is not equal to 0, it implies a minus b is equal to 0, which is equal to a is equal to b. यहाँ पे हमें इंटीग्रल डोमेन की डेफिनेशन की जरूरत थी 1 1 प्रूव करने के लिए. नाउ phi is a homomorphism, a ring homomorphism शो करने के लिए हम देखते हैं phi of a plus b is equal to a plus b x comma x, which is equal to ax plus bx comma x. ये हमें किसकी इक्वल शो करना है? phi of a plus phi of b, which is equal to ax comma x plus bx comma x, which in turn is equal to ax into x plus x into bx comma x into x, that is a x square plus b x square comma x square, which in turn implies ax plus bx comma x, because you can see by the relation we have defined that these two equivalence classes will be equal, and hence we have got that phi of ab is equal to phi of a plus phi of b. अब अंडर मल्टीप्लिकेशन देखने के लिए we need phi of ab is equal to abx comma x, and whereas phi of a dot phi of b is equal to ax comma x dot bx comma x, which in turn implies ab x square comma x square similarly is equal to abx comma x, and therefore phi of ab is equal to phi of a into phi of b, and hence we claim that phi is 1 1 ring homomorphism, and therefore phi is an embedding map, that is D can be embedded into F, where D was an integral domain and F was field. Therefore integral domain can be embedded into a field. जो हमने ये field above define किया है, that is F is equal to A comma B equivalence classes where AB belongs to D and B is not equal to 0, and ये जो equivalence classes हैं वो कैसे related है? A comma B is related to C comma D if and only if AD is equal to BC. इसको हम क्या कहते हैं? Field of quotients और quotient field of D. इसको हमें quotient ring के साथ कंफ्यूज नहीं करना है, because it is not equal to the quotient ring. It is known as field of quotients और quotient field of D. इस notation की जगह हम sometimes ये notation भी use करते हैं, that is A over B to denote the equivalence class of A by B. Logic इसके पीछे just यही है that if we consider an embedding of Z into Q, it would look like this. In fact, at times this notation looks more natural and convenient. For instance, A, B plus C, D is equal to AD plus BC, BD. ये कहाँ से आया हमारे पास? A over B plus C, D is equal to cross multiplication BC over BD, LCM basically. Therefore, this quantity is here and BD quantity is here. And similarly, A, B equal to C, D would imply that A over B is equal to C over D, that is AD is equal to BC. We can say that an integral domain D can be enlarged to a field F so that each element of F can be expressed as a quotient of two elements of D. An integral domain D can be enlarged to a field F so that each element of F can be expressed as quotient of two elements of D. Thank you.